So we consider some example. Using the definition of surface integral, we can establish some interesting result. Suppose this result is called invariance. Suppose A is a 3 by 3 orthogonal metric. And F is a surface in R3. And let S tilde be the image of S and A. You have a surface in the space. Applying an orthogonal transformation, you will obtain a new surface. The new surface S tilde has the same shape and the same quantitative properties which S. For example, their area should be the same. Of course, this need to be proved. Okay. Now we have a function f continuously defined over S, and we also define a new function f tilde is the composition of f which is the inverse of our orthogonal matrix. The orthogonal matrix defined a linear linear transformation of R3. So we compose the linear transformation, the inverse of the linear transformation, which our function f. We obtain a new function. Okay, so this f tilde is a function from S tilde to R, right? For if y in S tilde, then the inverse of y in S. Therefore, you can apply the f a inverse of y. Therefore, this function makes sense. Okay. Every point on S tilde, the pre-image under A is a point on S. Therefore, we can apply f to that point to get real numbers. So this function makes sense. The conclusion is that the integral equals the integral of f over S equals the integral f tilde y. Okay. So this is what we call the invariance. That is, you applied an orthogonal transformation to a surface. In the same time, you apply the orthogonal transformation to a function. You move the surface to another place, and correspondingly, you move the function to that place. The surface integral remained unchanged. Okay, so this is why we call this result invariance. And also, I will say some words about notations. Previously, we denote surface integral by this, or this is actually x1, x2, x3, because S is a subset of R3. Therefore, every point on S has 3 coordinates. Okay, so this is our previous notation. Of course, if you like, you can also write f x y z d sigma. But this notation is very clear to tell us that our integral is over a 2-dimensional object, the surface. But in our theoretical study, the double integral sign is not very convenient. Therefore, sometimes, in particular in the theoretical study, we prefer to use the single integral sign to denote the surface integral. Okay, so this is some words about notation. And now we explain this result, what we will prove geometrically. So this is a surface, maybe. So this is a surface S. You applied a transformation A. You obtained a new surface. And you have a function defined on S to R. So the composition of this is the inverse of A. The composition of the inverse of, so this is S theta. The composition of the inverse of A, that is A inverse, which F is a new function defined on S theta. This function we denoted by F theta, composed with A inverse. So our theorem, our conclusion says that integrating F over the surface S equals integrating the new function F theta over the image of S under the orthogonal transformation A. Okay, so this is the geometric meaning of this result. So how to prove this result? To prove this result, we applied the definition of surface integral. So we need to take a parametrization of the surface. Okay. So prove that this is a parametrization of S. So so this is S. We have a parametrization R from U, and then we have an A. This is S theta. Then this map the composition. Then C, the composition of A and R, that is a map from U to R3, is parametrization of the new surface S theta. Okay, so by the chain law, we need to compute phi U and phi V. Why we need to compute this? Maybe we denote by U1, U2. The point in the parametrization space is denoted by U1, U2. So phi U1, why we compute phi U1? Because when you compute the surface integral over S theta, you use the parametrization phi we defined here. You need to compute this quantity phi U1 plus phi U2. Unlike the previous argument, we should not use UV to denote the parameters of the surface. We use U1 and U2. Instead of U and V, we use U1 and U2. This is not material, not essential. Okay. So so this is why we need to compute the partial derivative of phi with respect to U1 and also U2. Now we compute phi U1. Phi U1 by the chain law. By the chain law, because phi is the composition of these two maps. So phi prime. Where to write? Phi prime U is A prime RU R prime U. But A is a linear map. A is linear, so A prime is A itself. So this is A R prime U. Okay, so this equality, if you write both sides are 3 rows 3 by 2 matrix. This is an inequality for 3 by 2 matrix. Okay? Because phi is from 2-dimensional to 3-dimensional. R is also from 3-dimensional to 2-dimensional to 3-dimensional. And A is a 3 by 3 matrix. So both phi prime U and R prime U are 3 by 2 matrix. So A is a 3 by 3. So the matrix on both sides of this equality are 3 by 2 matrix. So it has 2 columns. The 2 columns is precisely phi prime U1, phi prime U2 is A R U1 R U2. Okay, so we have this equality. This is a 3 by 2 matrix. We write the 2 column. This 3 by both 3 by 2 matrix can be written by column, and of course we can also A R U1 A R U2. Okay, so compare the columns, compare the first column and the second column, we will obtain what we need here. Therefore, phi derivative of phi which is with respect to U1 equals A R U1, and which is with respect to U2 equal A R U2. So we compute the derivative. Next, we shall compute their cross product. We shall compute their cross product. The cross product U1 cross phi U2. This is AR U1 cross AR U2. By the geometric meaning of cross product you can use is a vector orthogonal to RU1 and RU2. The cross product of RU1 and RU2 is a vector orthogonal to both of them, and which the norm equal to the norm of the product of their norm, and multiplying sine theta. Theta is angle between RU1 and RU2. And because orthogonal transformation does not change norm, does not change angle between two vectors. So using this, you will see that this is precisely A RU1 cross RU2. That is, you apply A first and then taking cross product equals you apply the cross product and apply A to the resulting vector. This is true only for orthogonal matrix A. If A is not orthogonal, this is not true. But this is true for orthogonal matrix A, because orthogonal matrix represent an orthogonal transformation which will not change the norm of vector, and also will not change the angle between two vectors. So by the geometric meaning of by the geometric meaning of cross product, you will obtain this equality. Okay, so this is very important. Having obtained this, our result, the invariance property of our surface integral follows immediately. Let's go to next page. So the integral over s theta of our function, by definition, because s theta has a parametrization phi, so this is f theta phi u, then phi u1 cross phi u2 du. Since u is u1, u2, so du is the means double integral. Now f tilde is f composed with phi a my inverse, and the phi is a and r. Then acting on u. Okay, so this part can be written in this way, because f tilde is f composed with a inverse, and the phi is the composition of a and r, and this the norm of phi u1 cross phi u2 by our previous computation. Phi u1 cross phi u2 is a multiplying the vector ru1 cross ru2. So this is a ru1 cross ru2, then du, right? And this is u. The composition fa inverse ar is f r u. And what's the norm? Because orthogonal transformation does not change the norm of the vector, so the norm of a acting on ru1 cross ru2 is precisely the norm of ru1 cross ru2. So this is ru1 cross ru2 du, and this can be written as ru1 cross ru2 du. So this is precisely the integral over S of the function f. So this proves our result. Okay, so this proof is actually very simple. Just combine your geometric imagination. In particular, this part of computation seems very easy using the geometric idea, using the geometric interpretation of cross product of two vectors, and also apply the property, the nice property of orthogonal matrix, or the nice property of orthogonal transformation represented by the orthogonal matrix A. Okay.